I will talk about this calculation that appears in a paper which is joint with Jonas Bergström, Adrian Diaconi, and Craig Westerland. And this is actually part of a larger project. So there's a follow-up paper to this one, which is joint with Jeremy Miller and Peter Patst and Oscar Randall Williams. And the goal of these two papers together is to prove a theorem in analytic number theory. And the statement that we prove is that something called the Connery, Farmer, Keating, Rubinstein, Snaith predictions are true for a family of L functions, the quadratic family over a function field in one variable over a finite field. And these CFKRS predictions, they are about something called moments, and you can verify them for the first or second or third moment, and this has been done by people in different situations before, but this is the first family where you can establish that this is true for all moments. But I will not talk more about that actually. I will just talk about this thing, this calculation of stable homology that goes into it. And one reason I chose to do this here is that when I've talked about this in other contexts, I've sort of avoided going into all of the higher structures that go into the proof. And now I'm in a situation where I can dig deep into those higher structures instead, and it's I think the nicest part of the paper, so I will just do that instead. And if you want to hear more about how this is related to analytic number theory, you can talk to me afterwards. So let me start by setting up the stage. So by gamma gn, I will denote the mapping class group. Of a genus G surface with n boundaries. And I will denote by beta n the braid group of n strands. And there are interesting homomorphisms from the braid groups to the mapping class groups. And they go like this. So you start with a braid on 2G plus 1 strands, and you land in the mapping class group of a genus G surface with one boundary. And let me tell you in words what this homomorphism does. So this is the fundamental group of the configuration space of 2G plus 1 points in a disk. And when I have 2G plus 1 points in a disk, I can take the unique branched double cover of the disk, which is branched at these 2G plus 1 points. And the Riemann-Hurwitz formula tells you the genus of the surface that you get upstairs. Its genus is G, and it's going to have one boundary component. The disk has one boundary, and since I have an odd number of punctures, I get a non-trivial double cover of that boundary disk, so I have one boundary disk upstairs as well. And that gives me a map of moduli spaces, if you will, from this moduli space of points to this moduli space of surfaces. And on fundamental group, it recovers this thing. And if I have an even number of points in the disk, the same construction works. Now, the monodromy along the boundary disk is instead trivial. So I get two disks upstairs, and this lands in gamma G2. And actually, there's a commuting diagram like so, where here I take the evident inclusion, and here I glue on a pair of pants. So I start from a... Is this too tiny? I think it is. But anyway, I start from this genus G surface. I glue on a pair of pants, and I get a surface of the same genus, but now with two boundaries. And I can continue this diagram. And here I glue on a pair of pants in the opposite direction. And this goes on. And now there are some common features of that column and that column. So both columns enjoy homological stability. So when you increase the number of punctures, you can take the homology of the braid groups and you see homological stability. And also here you're increasing the genus of the mapping class group. And this is due to Arnold for the braid groups and Harrer for the mapping class groups. And these works have been improved by many other people in subsequent work. You can say more. Both sides assemble to an E1 algebra. And here I don't mean the groups themselves, but rather their classifying spaces. So if I take the disjoint union of all of the classifying spaces of the braid groups, that's not just an E1 algebra, it's an E2 algebra in the evident way. Here, it's a bit more subtle because I'm using both surfaces with one boundary and two boundaries. It's not what you are perhaps used to. And in that case, it's actually a relatively recent construction that appears in a paper of Har, Wistrup, and Natalie Wahl. So you can take the disjoint union of all of these classifying spaces and you give it a very funny monoidal structure by gluing together two boundary intervals in a funky way. Which you do, and it turns out that that's an E1 algebra. It's actually not an E2 algebra. But you can do it. And this is then a homomorphism of E1 algebras. And you can study the respective group completions. In both cases, they're going to group complete some loop space. Because they're E1 algebras. And the group completion theorem tells you that the stable homology is the homology of that loop space. And the group completions are loop 2, S2, and this infinite loop space. Loop infinity of this Madsen-Tillman spectrum. And this is due to Madsen and Weiss. This was their proof of the Mumford conjecture. This is originally due to Seagull, and this was then generalized much further in Cohen, Lada, May. And the modern perspective is that this is the free E2 algebra on a point, and this is the free group complete E2 algebra on a point. And if you want, you can think of this as hyperelliptic Madsen-Weiss. You can think of this Arnold theorem as hyperelliptic Harrer stability. If you want to be degenerate about it, because you can identify the braid group with a hyperelliptic mapping class group in these cases. So the hyperelliptic mapping class group of a surface with one or two boundary components is precisely the braid group. And where is that one? Now we can decide to augment this diagram a little. So I can consider this map that assigns to a mapping class its action on the first homology of the surface. And I can do the same here, and the homology of this surface has rank 2g plus 1 z. These horizontal arrows are not surjective, not at all, because there's a symplectic form on homology which is preserved. If I replace this with a symplectic group, sp2gz, and I replace this with something funny called the odd symplectic group that was introduced by Gelfand and Zelevinsky, then actually these arrows are surjective. And you can make the even and odd symplectic groups into an E2 algebra in a funny way, which is a bit unexpected. But that's not really going to play any role today, but it's important for the larger project that we have this structure. Anyway, once I have this map, I get a large supply of interesting representations of both the mapping class groups and the braid groups, coming from any algebraic representation of the general linear group. So I'm going to pick a Schur functor, S lambda, which means precisely that S lambda of V is given by the following formula. So I take the n-fold tensor power of V, I tensor of the symmetric group with some irreducible representations of the symmetric group, and everything happens over a field of characteristic 0. And yeah, remember that irreducible representations of the symmetric group and characteristic 0 are indexed by partitions. And for each Schur functor S lambda, I get a consistent sequence of representations of all of the general linear groups, and I can ask what is the cohomology of the mapping class groups or the braid groups with those coefficients. So Loyenga and Randall-Williams compute a stable cohomology of the mapping class group with coefficients in such a Schur functor. And Loyenga did this before the Mumford conjecture was proven, but he did it assuming the Mumford conjecture. And then Randall-Williams gave a different proof, which is somehow cleaner, and it's the proof that we're going to adapt. And you could call this the twisted Mumford conjecture if you want. And the goal of this talk is to compute the stable cohomology. Actually, let me switch to homology. It's not going to matter. With these same coefficients coming from Schur functors. And you might call this the twisted hyperelliptic Mumford conjecture. So before I can formulate the theorem that computes this stable homology, I have to do some preliminaries, because the formulation is in terms of the algebra of symmetric functions and infinitely many variables, which I think several people in the room know, but also several people in the room do not know. So let me talk about it. Okay, so capital lambda is the ring of symmetric functions in infinitely many variables. And this lambda is a graded ring. And the key property is that lambda n, the degree n part, is isomorphic to the representation ring of the symmetric group, which is by definition the Grothendieck group of the category of finite dimensional representations of the symmetric group in characteristic 0. And the basis for lambda as a free abelian group is given by the Schur polynomials. And the Schur polynomial S lambda corresponds under this bijection to the irreducible representation indexed by the partition lambda. So for example, this partition indexes the trivial representation of Sn, and this partition indexes the sign representation of Sn. And it's a ring, and the multiplication is given by the induction product. So if I take a representation of Sn and the representation of Sm, I can induce to Sn plus m. It's Day convolution. And I will also need the completion, which is just the product of its graded pieces. Now recall that a symmetric sequence means a sequence of representations of each symmetric group. And I will consider representations in graded vector spaces or vector spaces by default. And if V is a symmetric sequence, then I will denote by bracket V its class in lambda hat. So I have a sequence of representations, and each of them defines an element in this representation ring. And if I'm in, let's say this is in vector spaces, and if I'm in graded vector spaces, then I might consider instead this in a polynomial ring where T keeps track of the grading. Or if it's possibly non-positively graded, I will take a polynomial. And I will just write bracket V, and I will not really be very careful about where it lives. But T always keeps track of homological degree. Now, a symmetric sequence gives rise to an analytic functor which I will write as fv of x So for example, if V is the underlying symmetric sequence of an operad, this is the free algebra functor over that operad. And if all but finitely many of these V's are 0, I will call such a thing a polynomial functor for obvious reasons. Maybe I should comment that I'm using the words analytic functor and polynomial functor, but I'm doing something more naive than we saw half an hour ago in Vespa's talk. Everything here is semi-simple. and everything happens in characteristic 0. And I can be very sloppy with how I define polynomiality, and I don't have to be careful at all at any point. And we call this guy V. The Taylor series of this analytic functor. And an analytic functor is uniquely determined by its Taylor expansion. Now, if I have two analytic functors, and I compose them, I get again an analytic functor, and the corresponding symmetric sequence is exactly the composition product of symmetric sequences. Which I think most here have seen. Operads are monoids in this category of symmetric sequences with respect to the composition product. If you haven't seen it, I'll take it on faith that you can look at this expression and think very hard, and you realize what the formula for the composition product has to be. And if you decategorify this statement and look instead at the Taylor series, you see that the Taylor series of V yeah, this looks a bit funny now. But here I do an operation called the plethism. And here I do the composition product. And plethism is a binary operation on this ring of symmetric functions. So this is a roundabout way of saying that, well, there is this composition product on symmetric sequences, which, if you haven't seen it before, it's actually not exotic, because it just corresponds to composition of analytic functors. And this composition product of symmetric sequences, under this isomorphism of the Grothendieck ring of symmetric sequences and lambda hat, it corresponds to a binary operation on lambda hat, and it is exactly this thing called plethism that was introduced by Littlewood in the 40s. And yeah, plethism is a binary operation on lambda. It doesn't quite extend to a binary operation on lambda hat, in the same way that composition of two power series is generally not a power series. You need the second one to have vanishing constant term. And the same is true here. For this to be meaningful, you should either insist that this one is finite or that one has vanishing constant term. So let's do an example. So we consider the operad com. It has an underlying symmetric sequence, which is just a trivial representation in each arity. It has an associated analytic functor. And, well, we can stare at this formula and we see that, well, we take all tensor powers and we tensor with a trivial representation. That means we take the symmetric algebra. Which also matches what I said before, that FV is the free V algebra if V comes from an operad. So this would be an example of an analytic functor. And this particular analytic functor will be important. And I make the following definition. So if I have an element in lambda hat, which has vanishing constant term, then I define exp of x to be this plethism. So this exponential is the functor, the operation that corresponds to taking the symmetric algebra. And this was introduced by Getzler and Kapranov in their paper on modular operads, and they call this the plethystic exponential. And the very useful fact is that exp is invertible with inverse a certain map log that now takes as its input something with constant term 1. And returns a power series with a vanishing constant term, so to speak. Oh yeah, sorry. And I think this is due to Getzler and Kapranov, but they attribute it to Cadogan from the 70s, a paper in combinatorics. And I can actually give the proof. Well, exp was given by Petersen with this com. Now, if I think about com composed with a shifted Lie operad, well, com is Kosul and shifted Lie is its Kosul dual. Yeah.
Sorry, for you, com is unit or not?
For the moment, yeah, okay. Let me remove the unit here. Com 0. Yeah. So yeah. So this was unital. This is non-unital. Yeah, that's a good point. And now this. It admits the Kosul differential, so I can put the differential on it, which makes this a symmetric sequence of chain complexes, and it's acyclic in all positive arities, except arity 1.
So that could be the root differential, you might want to dualize one of them. It doesn't matter.
It doesn't matter, it's all finite. And yeah, we all know what's going on. And now if I take this Taylor series and I disregard this grading parameter t, and instead when I take a graded vector space I just take the alternating sum of the dimensions. It follows that I have this formula. But then that means that taking the plethism with com is invertible, because this is a monoidal, this is the unit object in the monoid. And if I have a one-sided inverse, it's a two-sided inverse. And yeah, so the log of 1 plus x is actually just shifted Lie composed x. And that's the proof. Let me give one example, which will come back later. So consider V goes to A of V, and I suppose that this is an analytic functor. To connected co-commutative Hopf algebras. Well, then I can get a new analytic functor by taking primitives. And The Milnor-Moore theorem says exactly what the relationship between these two is. Namely, I compose this functor with the universal enveloping algebra functor, and I get that one. And now Poincaré-Birkhoff-Witt theorem tells me that universal enveloping algebra functor is the same as symmetric algebra functor when I just think of it as an analytic functor. So that tells me that this Taylor series is the exponential of that Taylor series, which now is equivalent to saying that the primitives are the logarithm of A. So that's Poincaré-Birkhoff-Witt and Milnor-Moore. And now let me state the theorem that we prove. So write down the generating series. Like so. And then we need a variable that keeps track of the homological grading. And then we need a Schur polynomial, and we're actually going to transpose the Schur polynomial. And this is given by the plethystic exponential applied to T inverse of the plethystic logarithm of 1 plus T plus sum over all k bigger than 0, trivial representation of the symmetric group S2k, T to the power k minus 1, end parentheses. So this is a very, I should say here, that's the theorem from our paper. And this is very computable. It's maybe not so easy to stare at this formula and say what any particular homology group is, but you can feed it into Sage, and it will tell you lots and lots of Betti numbers. And you can prove some structural properties, like it vanishes in this region or whatnot. And this functor that we write down here, x blog, blah, 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 was actually written down before in connection with this CFKRS moment problem by analytic number theorists. They didn't write it in terms of the plethystic exponential and the plethystic logarithm. What they did was, when you have this power series in infinitely many variables, you can specialize it to finitely many variables. And then it converges, and it's given by an Euler product. And they wrote down that Euler product as something that appears in this CFKRS recipe. And they call it the arithmetic factor, or the R function. And much of this work, it's been a super long project, but it was very productive. So Adrian, my co-author, was on sabbatical in Stockholm in the spring of 21. And we were stuck for a long time, but then we had two breakthroughs in a short amount of time. And the first was, we realized that this R function had this cohomological interpretation, and then we could actually prove this theorem. And that was the highlight of the spring of 21. So I thought I would. Yeah.
Am I right to assume, that V in this form is kind of V infinity, so it's the limit of the standard
Yes,
representation?
yes, exactly.
Right? Yeah.
Yes,
Okay.
yes. Absolutely right. Okay, so I will try to explain the strategy. And the strategy is an adaptation of this strategy of Randall-Williams that works for the mapping class group and uses the Madsen-Weiss theorem. So we want to somehow import Madsen-Weiss ideas. And here's what we're going to do. So let X be a based space with an action of the cyclic group of order 2. And Bn of X will denote the following. It's a configuration space of n points in a disk. Let's say the interior of a disk plus the additional data of, well, I look at the disk. I take the unique branched double cover over these n points. So I get this surface with one or two boundary components. And I take a C2 equivariant map to X. Yes?
I just wanted to, I'm a bit confused about this formula because you said that log you can apply to power series of the form 1 plus something.
Yes.
And there you apply it to the series of the form 1 plus t plus something.
Ah, yes. It also works. But you have to think about how does X and log act on T? Because I'm in a lambda ring and X and log act on the.
But I mean, for example, on the left I can put T. So you put minus T. So I don't have the right to put T equal to -1 or.
You cannot substitute T for anything. No. That's illegal.
Okay. Okay. So I cannot get Euler characteristics.
No, exactly. You cannot because, well, this has homology in infinitely many degrees. So the Euler characteristic is not defined.
Ah, great.
Yes. So X is a based C2 space. Y has a C2 action because it's a double cover of the disk, and I take a C2 equivariant map to X, and I insist that F maps the boundary of Y to the base point of X. And there's a vibration like so that forgets about the data of the map and just remembers the locations of the branch points. And this is a vibration. And the fiber is a mapping space. So I look at based maps, C2 equivariant, from this surface relative its boundary to X. And now I will do the trick of choosing X cleverly. So I take X to be Ka, which is my notation for a product of Eilenberg-MacLane spaces. So A, I will assume this to be a graded Q vector space. And then Ka is the following product. Yes?
Is sigma the same thing as y?
Sorry?
Is sigma the same thing as y?
Yeah. Yes. Let me change that to sigma. Oh. And I need a C2 action here, and the action is just by multiplication by -1 in this. So A has an action by -1, it's a vector space, and I do this. And now something wonderful happens, because let's think about what is this fiber in this case. So then I have, for any space that maps from W to Ka is homotopy equivalent to a product of Eilenberg-MacLane spaces, namely K of A tensor this thing. So, yeah, space of maps to an Eilenberg-MacLane space is always a product of Eilenberg-MacLane spaces in this way. And now I specialize to W is this sigma relative its boundary. And in this case, I only have two non-trivial reduced cohomology groups. I have H1, and I already have a name for H1 of my surface. I call that V. So I'm going to write V here. This is put in degree 1. Then I have H2, which is just Q, the trivial representation, so to speak. And I write it like so. But now I should also take C2 equivariant maps. And what happens here, plus minus 1 acts on A as multiplication by minus 1. It acts on V as multiplication by minus 1 as well. Because hyperelliptic involution acts as multiplication by minus 1 on the first homology of this guy, or first homology. So C2 acts trivially on this guy, and it acts as minus 1 here. So when I take C2 fixed points, I get that. This goes away. And I'm left with the following fibration. And now I want to analyze this using the Serre spectral sequence. It turns out that the Serre spectral sequence degenerates immediately. One way to see that is that whatever the differentials are, they have to be equivariant with respect to the action of the general linear group, GL of A. And there is no room for any equivariant non-trivial differential in the spectral sequence. So equivariance just forces all differentials to be 0. And the consequence of the degeneration of the Serre spectral sequence is that the homology of the braid group with coefficients in this product of Eilenberg-MacLane spaces is the same as the homology of B and Ka. And what is the homology of this? We're working rationally, and we know the rational homology of Eilenberg-MacLane spaces. So this is a symmetric algebra on A tensor B shifted by 1. Now we have to remember how to calculate the symmetric algebra of a tensor product. This is called the Cauchy identity. And it's a sum over all sure functors, S lambda of A, tensor S lambda of B shifted 1. And I can clean this up. If I take the Kosul sign rule into account. So I'm taking homology of the braid group with coefficients in this group, which is the same as that group. But S lambda of A is actually not a representation of the braid group, so I can just pull that out. So I see that the homology of Bn Ka is the sum over all lambda, S lambda of A, tensor homology of the braid group, S lambda transpose of V. And here I should take plus size of the partition. And what does this mean? Well, it means that this is an analytic functor. You see, A, I assign that this homology group, I've manifestly written it as an infinite direct sum of Schur functors, and that is what an analytic functor is. So here's my expression, but this is even better because the Taylor coefficients of this analytic functor, that's the homology groups we're trying to compute. And now if I can calculate these Taylor coefficients by any other means, and I can equate the two series, and then I would have a calculation of the stable homology that I want. And there's going to be possible to do this in the stable range, which then gives the result. And the idea is to sort of exploit locality, which is, it's a circle of ideas coming out of the Madsen-Weiss theorem. It has many names. People talk about scanning and H principle, and all these things sort of fit together in some way. And I will talk about this locality idea in kind of a baby case where I calculate that the homology of the braid groups is given by loop 2S2. So the idea is, I'm going to look at how do you prove that the group completion of this E2 algebra is loop 2S2. Then I'm going to replace conf n of D with this space, Bn of x, and I'm going to repeat the argument suitably modified, and I'm going to get some different twofold loop space, whose homology I can calculate and show to be an analytic functor of A, whose Taylor series is written here. That's a strategy. Yes.
About this. So on the board that you are now hiding,
Yes.
there is a shift by the number of boxes in lambda.
Yes.
And I don't quite see it over there.
Well, there are many shifts involved in deriving this formula.
Okay, so it's some kind of miraculous change, because it looks almost like left-hand side, right? That formula up.
Oh. Yes. Well, you can re-index. You can put the shift. I put the shift on V, but I can put the shift in A instead. Anyway. So let's write down an idea. It's really sort of a fairy tale. So I'm going to think about this functor. Phi of u goes to discrete subsets of u. This is a sheaf of topological spaces on open subsets of the plane. And you can think about what are compactly supported sections of this sheaf, where I mean that outside of a compact set, I take the value which is the base point, which is the empty subset. And I just get the disjoint union of all configuration spaces of points. Now in sheaf cohomology, compactly supported sections are dual to ordinary sections. But that's in an abelian setting, and it's on a manifold, but C is a manifold. What happens in this non-abelian setting, and to get a feeling for what the answer is, you can think about what algebraic structure does it support if phi is some sheaf. So if phi is a sheaf, then compactly supported sections is an E2 algebra in exactly the same way that this is an E2 algebra, because I have some smaller disk inside of a disk, and I have a compactly supported section in each smaller disk, and I just extend by 0. But I can also take usual sections, and this is now an E2 co-algebra. Because if I have a section on a disk, I can restrict it to a bunch of smaller disks inside of that disk. And this maybe suggests that Poincaré duality should play the role of Koszul duality between these two. This E2 algebra and this E2 co-algebra. And this is indeed the case. So if phi is sufficiently connective, then this E2 algebra would be given by the twofold loop space of this guy, and this will be the twofold bar construction of that guy. And I don't know exactly how to attribute this idea, but I think it's Ayala Francis. And in this case, we're not in a sufficiently connective situation. This is a disconnected space. And we don't find that this is literally a double loop space, but its group completion becomes that double loop space. So what happens is that you group complete it and you get loop 2 of gamma C phi. And you can show this to be homotopy equivalent to S2. And it's a very concrete deformation retraction. So if you have a discrete subset of a disk, you look at what's the largest disk centered at the origin, which contains at most one configuration. There is some such disk, and you just restrict to that disk. And if your configuration consists of at most one point, that's the identity. And it deformation retracts everything down to the subspace where you have at most one particle. But that's S2, because either you have one particle or you have the empty particle, which plays the role of one-point compactifying. So you have at most one particle, and it's topologized in such a way that if you have a particle, it can vanish by wandering off to infinity. So this fairy tale gives you one way of seeing that this group completion is that thing. And now I want to do the same for this sheaf psi. So BUX parameterizes a discrete subset of U, and then a C2 equivariant maps from the associated double cover to X. And When I take compactly supported sections, I get that guy. And if I take not necessarily compactly supported sections, it deformation retracts to at most one particle. So the subspace where I have at most one particle, and then I have the branch double cover. Same deformation retraction. And that's going to be my twofold delooping that I want to analyze. I'm speeding up more and more, and I'm going to speed up even faster now. So I claim that there's a push-out diagram, a homotopy push-out diagram. Like so. And how does this work? Well, I can cover this subspace with at most one particle by two pieces. Here I have exactly one particle. Here I insist that I have no particle near the origin, and that actually deformation retracts to the subspace where I have no particle at all by radial expansion. And here I have one particle near the boundary of the disk. And let's just do one of these. Suppose I have exactly one particle in the disk, then my branch double cover is just a disk mapping to a disk. And then I have a map from X to C2. So I have my disk. Sorry, I messed up. This is the subspace where I have exactly one particle. Yeah, so I have my disk. I have my 2-to-1 cover. And I have the map to X. Now there's a fixed point for the hyperelliptic involution in the middle of this disk. And that has to go to something in the fixed locus. So C2 fixed point. And now I can just deformation retract everything down to its origin to make this map constant. But now there is also the value, the action of the hyperelliptic involution that I have to take the quotient of, and that gives me this thing. And the analysis of these two are similar. And now, here I have this very concrete homotopy push-out diagram. I take X to be this Eilenberg-MacLane space. And when it's an Eilenberg-MacLane space, I'm going to see that this space becomes something quite simple when I invert the prime 2. I get S2 wedge this algebra. So I want to understand this analytic functor because everything that I said so far tells me that the Taylor coefficients of that analytic functor are the same as the Taylor coefficients that I obtained here. And now, here's what you do. This space is a Koszul space in the sense that was introduced by Alexander. And these are the spaces for which it's easy to compute loop space homology. And it's easy to write down the cohomology ring of this space and the quadratic presentation. You take the dual presentation, and that gives you, after a degree shift, what's written inside here, inside the exponential. That's now the homology of the loop space, because it's a quadratic dual. Now I take the logarithm, and the example is still written here. That gives me the rational homotopy of the one-fold loop space. I divide by t, which shifts degrees by 1. That gives me now the homotopy of the two-fold loop space, and I exponentiate. And that gives me the homology of the double loop space. Except I had to subtract 1, and that's because I only want the base component. And pi 0 is z, and this 1 is a generator of pi 0. That's it. My time is up. Sorry for going over time.
Questions?
Yes. So the right-hand side, the adds P inverse log, it makes one think of the symmetric sequence of Gerstenheimer related on something. So are you saying that this is a free E2 thing?
It's not quite a free E2 thing.
But it looks like it.
It looks like it, yeah, but it does come from quadratic duality of Gerstenheimer algebras. Mm-hmm. So I can take the cohomology ring of this guy. I can think of that as a Gerstenheimer algebra with trivial bracket, and its quadratic dual is this homology. But this is, has non-trivial multiplication, so its dual is not free, but I do have a simple quadratic presentation. And that's actually very important. We use that to compute the Galois action on the homology in the étale setting. That we only have to calculate the Galois action on the Gerstenheimer indecomposables, and they are very simple because they are dual to the generators here.
Great.
More questions? Is it easy to see how L functions play a role here, or is it?
So the L functions are L functions of curves over a finite field. And they can be interpreted as, there's a cohomological interpretation via the Grothendieck-Lefschetz trace formula in terms of trace of Frobenius on étale cohomology. And what's going to happen here is that we calculate this homology in characteristic 0, but then there's a comparison isomorphism that tells you that it's the same as the homology, étale homology, if you take this over a finite field. And the family of L functions that we're interested in is the family of all L functions attached to hyperelliptic curves over this finite field. And these are exactly the things parameterized by this hyperelliptic moduli space, whose fundamental group is the braid group.
Thank you. More questions? If not, let's close the session and thank the speaker.